Hello friends, in our previous lecture we discussed the sinusoidal voltage and current values, the angular measurement of a sine wave and the sine wave formula. In today's lecture we shall be talking about phasors and its use to represent a sine wave, how phasors are related to the sine wave formula, draw a phasor diagram, discuss angular velocity, use complex numbers to express phasor quantities, describe the complex plane, represent a point on the complex plane, discuss real and imaginary numbers, express phasor quantities in both rectangular and polar forms, and finally convert between rectangular and polar forms. Introduction to phasors. Phasors provide a graphic means for representing quantities that have both magnitude and direction, that is angular position. Phasors are especially useful for representing sine waves in terms of their magnitude and phase angle, and also for analysis of reactive circuits. You may already be familiar with vectors in maths and science. A vector is any quantity with both magnitude and direction. Examples of vectors are force, velocity and acceleration. The simplest way to describe a vector is to assign a magnitude and an angle to a quantity. In electronics, a phasor is a type of vector, but the term generally refers to quantities that vary with time, such as sine wave. Examples of phasors are shown in this figure. The length of the phasor arrow represents the magnitude of a quantity. The angle theta represents the angular position as shown in part A for a positive angle. The specific phasor example in part B has a magnitude of 2 and a phase angle of 45 degrees. The phasor in part C has a magnitude of 3 and a phase angle of 180 degrees. The phasor in part D has a magnitude of 1 and a phase angle of 45 degrees or plus 315 degrees. Notice that positive angles are measured counterclockwise from the reference and negative angles are measured clockwise from the reference. Phasor representation of a sine wave. A full cycle of a sine wave can be represented by rotation of a phasor through 360 degrees. The instantaneous value of the sine wave at any point is equal to the vertical distance from the tip of the phasor to the horizontal axis. This figure here shows how the phasor traces out the sine wave as it goes from 0 degrees to 360 degrees. You can relate this concept to the rotation in an AC generator. Notice that the length of the phasor is equal to the peak value of the sine wave. The angle of the phasor measured from 0 degrees is the corresponding angular point on the sine wave. Phasors and the sine wave formula. Let us examine a phasor representation at one specific angle. Figure shows a voltage phasor at an angular position of 45 degrees and the corresponding point on the sine wave. The instantaneous value of the sine wave at this point is related to both the position and the length of the phasor. As previously mentioned, the vertical distance from the phasor tip down to the horizontal axis represents the instantaneous value of the sine wave at that point. Notice that when a vertical line is drawn from the phasor tip down to the horizontal axis, a right triangle is formed. The length of the phasor is the hypotenuse of the triangle and the vertical projection is the opposite side. From trigonometry, the opposite side of a right triangle is equal to the hypotenuse times the sine of the angle theta. The length of the phasor is the peak value of the sinusoidal voltage V peak. Thus, the opposite side of the triangle, which is the instantaneous value, can be expressed as V is equal to V peak sin theta. Recall that this formula is the one stated earlier for calculating instantaneous sinusoidal voltage. A similar formula applies to a sinusoidal current, where I is equal to I peak into sin theta. Positive and negative phasor angles. The position of a phasor at any instant can be expressed as a positive angle, as you have seen, or as an equivalent negative angle. Positive angles are measured counterclockwise from 0 degrees. Negative angles are measured clockwise from 0 degrees. For a given positive angle theta, the corresponding negative angle is theta minus 360 degrees. In part B, a specific example is shown. The angle of the phasor in this case can be expressed as plus 225 degrees or minus 135 degrees. Phasor diagrams. A phasor diagram can be used to show the relative relationship of two or more sine waves of same frequency. A phasor in a fixed position is used to represent a complete sine wave, because once the phase angle between two or more sine waves of the same frequency or between the sine waves and a reference is established, the phase angle remains constant throughout the cycle. For example, the two sine waves in figure A can be represented by phasor diagrams as shown in part B. As you can see, sine wave B leads sine wave A by 30 degrees and has less amplitude than sine wave A, as indicated by the lengths of the phasors. Angular velocity of a phasor. As you have seen, one cycle of a sine wave is traced out when a phasor is rotated through 360 degrees or 2 pi radians. The faster it is rotated, the faster the sine wave cycle is traced out. Thus, the period and frequency are related to the velocity of rotation of the phasor. The velocity of rotation is called the angular velocity and is designated omega. When a phasor rotates through 2 pi radians, one complete cycle is traced out. Therefore, the time required for the phasor to go through 2 pi radians is the period of the sine wave. Because the phasor rotates through 2 pi radians in a time equal to the time period t, the angular velocity can be expressed by this expression: omega is equal to 2 pi over t. Since f is equal to 1 upon t, omega becomes equal to 2 pi f. When a phasor is rotated at an angular velocity omega, then omega t is the angle through which the phasor has passed at any instant. Therefore, the following relationship can be stated: theta is equal to omega t. Substituting 2 pi f for omega results in theta is equal to 2 pi f t. With this relationship between angle and time, the equation for the instantaneous value of a sinusoidal voltage V is equal to V peak sin theta can be written as V is equal to V peak sin 2 pi f t. You can calculate the instantaneous value at any point in time along the sine wave curve if you know the frequency and peak value. The unit of 2 pi f t is the radian, so your calculator must be in the radian mode. The complex number system. Complex numbers allow mathematical operations with phasor quantities and are useful in the analysis of AC circuits. With the complex number system, you can add, subtract, multiply and divide quantities that have both magnitude and angle, such as sine waves and other AC circuit quantities. Most scientific calculators can perform operations with complex numbers. As illustrated in figure, positive numbers are represented by points to the right of the origin on the horizontal axis of a graph, and negative numbers are represented by points to the left of the origin. Also, positive numbers are represented by points on the vertical axis above the origin, and negative numbers are represented by points below the origin. The complex plane. To distinguish between values on the horizontal axis and the values on the vertical axis, a complex plane is used. In the complex plane, the horizontal axis is called the real axis and the vertical axis is called the imaginary axis, as shown in figure. In electrical circuit work, a plus minus j prefix is used to designate numbers that lie on the imaginary axis in order to distinguish them from numbers lying on the real axis. This prefix is known as the j operator. In mathematics, an I is used instead of a j, but in electric circuits, the I can be confused with instantaneous current, so j is used. Angular position on the complex plane. Angular positions are represented on the complex plane as shown in figure. The positive real axis represents 0 degrees. Proceeding counterclockwise, the positive j axis represents 90 degrees. The negative real axis represents 180 degrees. The minus j axis is the 270 degrees point, and after a full rotation of 360 degrees, you are back to the positive real axis. Notice that the plane is divided into 4 quadrants. Representing a point on the complex plane. A point located on the complex plane is classified as real, imaginary, or a combination of the two. For example, a point located 4 units from the origin on the positive real axis is the positive real number plus 4, as shown in figure A. A point 2 unit from the origin on the negative real axis is the negative real number minus 2 as shown in part B. A point on the plus j axis 6 units from the origin as shown in part C is a positive imaginary number plus j6. Finally, a point 5 units along the minus j axis is the negative imaginary number minus j5 as shown in part D. When a point lies not on any axis but somewhere in one of the 4 quadrants, it is a complex number and is defined by its coordinates. For example, in this figure, the point located in the first quadrant has a real value of plus 4 and a j value of plus j4 and is expressed as plus 4 plus j4. The point located in the second quadrant has coordinates minus 3 and plus j2. The point located in the third quadrant has coordinates minus 3 and minus j5. The point located in the fourth quadrant has coordinates of plus 6 and minus j4. Rectangular and polar forms. Rectangular and polar are two forms of complex numbers that are used to represent Phasor quantities. Each has certain advantages when used in circuit analysis depending on the particular application. A Phasor quantity contains both magnitude and angular position or phase. Here italic letters such as V and I are used to represent magnitude only, and bold faced non-italic letters such as V and I are used to represent complete Phasor quantities. Rectangular form. A Phasor quantity is represented in rectangular form by the algebraic sum of the real value a of the coordinate and the j value b of the coordinate expressed in the following general form: a plus jb. Examples of Phasor quantities are 1 plus j2, 5 minus j3, minus 4 plus j4 and minus 2 minus j6. As you can see, the rectangular coordinates describe the Phasor in terms of its values projected onto the real axis and the j axis. An arrow drawn from the origin to the coordinate point in the complex plane represents graphically the Phasor quantity. Polar form. Phasor quantities can also be expressed in polar form, which consists of the Phasor magnitude c and the angular position relative to the positive real axis theta, expressed in the following general form: c angle plus minus theta. For example, figure shows 4 Phasors on the complex plane. The length of the Phasor, of course, represents the magnitude of the quantity. Keep in mind that for every Phasor expressed in polar form, there is also an equivalent expression in rectangular form. Conversion from rectangular to polar form. A Phasor can exist in any of the 4 quadrants of the complex plane as indicated in figure. The phase angle theta in each case is measured relative to the positive real axis, and phi is the angle in the second and third quadrants relative to the negative real axis as shown. The first step to convert from rectangular form to polar form is to determine the magnitude of the phasor. A phasor can be visualized as forming a right triangle in the complex plane as indicated in this figure for each quadrant location. The horizontal side of the triangle is the real value A and the vertical side is the j value B. The hypotenuse of the triangle is the length of the phasor C, representing the magnitude and can be expressed using the Pythagorean theorem as C is equal to under root A square plus B square. Next, the angle theta indicated in parts A and D of figure is expressed as an inverse tangent function, where theta is equal to tan inverse plus minus B over A. The angle theta indicated in parts B and C of figure is theta is equal to plus minus 180 degrees minus plus phi, which includes both conditions as indicated by the dual signs. Theta is equal to plus minus 180 degrees minus plus tan inverse B over A. In each case, the appropriate signs must be used in the calculation. The general formula for converting from rectangular to polar is plus minus A plus minus JB is equal to C angle plus minus theta. So friends, this brings us to the end of our discussion in this lecture, and therefore we sum up. In this lecture, we learnt about phasors and its use to represent a sine wave, how phasors are related to the sine wave formula, draw a phasor diagram, discuss angular velocity, use complex numbers to express phasor quantities, describe the complex plane, represent a point on the complex plane, discuss real and imaginary numbers, express phasor quantities in both rectangular and polar forms, and finally convert between rectangular and polar forms. So that is it for today. See you in the next lecture. Thank you very much.